Hello everyone, welcome back to Holi-Tech Academy. So in this part, that is fourth part, we'll be discussing these topics. That is electric dipole, dipole moment, conditions for dipole action, axial and equatorial points, derivation for electric field at an axial point and due to an equatorial point. And we'll also have a discussion on expression for torque. And then finally, time period of an electric dipole in an uniform electric field. Now let us start the discussion on a very important and interesting topic, that is electric dipole. Let's understand the definition of a dipole first. What is a dipole? Two poles, right? The definition of dipole states that two charges with equal magnitude, but they are opposite in nature and they are separated by a very small distance. Two equal two equal charges. Say for example, it is 3 coulombs and this is also 3 coulombs. But here it is positive charge and here it is a negative charge. So these two charges are having equal magnitude, but the nature is different, right? Here it is plus and here it is minus. Okay, two charges which are equal in magnitude but opposite in nature and they are separated by a very small distance is. Now let us understand a term here which is called as dipole moment, which is represented by small p. What is a dipole moment? It is a product of charge and the distance between two charges. Say for example, here our dipole plus q and here our dipole minus q is present and they are separated. What we have here, we have positive q and here we have negative q, but the value of q is same both here, but the sign is different. So dipole moment states that it is a product of the charge and the distance between these two charges, that is small d. Okay, the SI unit of dipole moment is coulomb meter and it is a vector quantity. Vector quantity states it has both magnitude as well as direction. Okay, now let us understand the next condition. Net charge of the dipole is 0. Say for example, we have our charge plus q and minus q. These two are dipoles, right? These two are electric dipoles. But if you add them, it will be plus q minus q, which is equal to 0. Again, if you consider plus 2q minus 2q, so the net charge is 2q minus 2q, which is equal to 0. So the sum of these two charges here it is 0. Whatever charge you can take. Even next condition, what does it state? Net electric field due to the dipole is not 0 because there are two different charges. That means, example, we have a charge plus q and we have one more charge minus q. The electric field produced by these two charge is because of the presence of the other two charges, right? So it experiences an electrostatic force because of its presence. So here q, whatever electric field is being caused because of the presence of charge q, it is experienced by minus q. Whatever electric field that is caused by minus q, it is experienced by this plus q. So the net electric, that means net electric field due to dipole is not 0. Okay, now let us understand what are the terms and conditions for understanding a dipole. Okay, all dipoles are measured from the midpoint of the dipole. Say for example, if this is our dipole plus q and minus q, okay, and they are separated by a distance d. Okay, this is our point midpoint o, and want to find the dipole at point p, it will be measured from midpoint itself. That means all the electric dipoles at any point, they are measured from the midpoint to that particular point where we want to consider our electric dipole. This is a condition for measuring an electric dipole. For example, here we have plus q charge and here we have minus q charge. They are separated by a distance. Say we can call it as d. And here if we have a point p which is lying outside, that is also measured from the center of this distance to this point p. The dipole at this point p is measured from the center of these two charges itself. Let us understand what is an ideal dipole. It consists of charges of high magnitude and they're separated by a very small distance. Say for example, here we have 10 coulombs and minus 10 coulombs and they're separated by very small distance, that is, say for example, 1 centimeter. Okay, that is an ideal dipole, which is having higher magnitude and they're separated by a very small distance. Now let us understand what is a quadrupole. Two dipoles that are linear arranged such that the like charges overlap. Say for example, there are two set of dipoles of same magnitudes. So minus q plus q plus q minus q. Okay, these two positive charges, they are overlapping, and these charges are linearly arranged. Both the charges are linearly arranged and positive charges overlap. This type of condition is called as a positive dipole, a positive quadrupole. And here in our next condition, we have plus q minus q, and here we have plus q, and here we have minus q. So in this condition, you can clearly see that the negative and positive, they are overlapping and they are linearly arranged. A condition where when two sets of dipoles, they are linearly arranged at that time, when unlike dipoles which are arranged in this pattern, when they are overlapping, this type of condition is called as a negative quadrupole. Now let us understand the terms axial points and equatorial points. This is plus q charge and this is minus q charge, and they are separated by a distance d, and point P is situated somewhere here, but it is on the same axis of these two dipoles. So this point is called, and this is an axial point. In case of this, say for example, we have a point plus q charge, and here we have a point minus q negative charge, and they are separated by a distance of, say, d. If our point P, it is lying on the perpendicular bisector, or it bisects the distance between these two charges, this is an equatorial point. Let us derive the expression for net electric field at an axial point due to a dipole. So now we'll derive the expression for the net electric field due to an axial point. So this is our axial point P, which is situated at the distance of x from the center, and this is our distance. Say if it is a, what is the distance from q to q? It will be 2a, right? Now let us suppose this is point A and this is point B, and this direction we will name it as point N. Okay, and PA is in this direction and PN is in this direction. We know that PA is in this direction. Therefore, electric field due to PA is equal to K into Q divided by x plus A the whole square. X plus A because this entire distance is x plus A. Now, this is acting along the direction PA. BP is acting in this direction, right? Therefore, the equation of electric field due to BP is equal to KQ divided by x minus A, because this is entire distance x and we have to subtract this distance A. So the point from B to P is x minus A. So it is acting along PN direction. Let us calculate the net axial electric field. We know that in this direction it is positive, this direction it is negative. So we PA, it is negative, this direction BP, it is positive. Therefore, E axial, that is net electric field due to an axial point, is EBP plus EBP minus EPA, which is equal to K into Q divided by x minus A the whole square minus K into Q divided by x plus A the whole square. Okay, if we take K and Q common, we are left with 1 divided by x minus A the whole square minus 1 divided by x plus A the whole square. Okay, if we calculate this, KQ x plus A the whole square minus x minus A the whole square divided by x minus A the whole square into x plus A the whole square. So if you calculate this, it will be K into Q into x square plus 2xa plus a square minus of x square minus 2ax plus a square divided by, can I write this as x minus a, x plus a the whole square Therefore, k into q in the bracket x square plus 2xa plus a square minus x square plus 2xa minus a square divided by x minus a and x plus a could be written as x square minus a square the whole square. Okay, we know that x square will get cancelled and a square will get cancelled. So we are left with k into q into 2xa plus 2xa will be 4xa divided by x square minus a square the whole square. So can we write k into q into 2 into 2 into x into a divided by x square minus a square whole square. So here di- dipole moment q into 2a will be dipole moment p. Therefore, it will be k into dipole moment which is 2 into q into 2a, that is dipole moment p, into 2x divided by x square minus a square the whole square. This is the equation for net electric field due to, this is an expression for net electric field at a axial point due to dipole. Now, now here we have a case when x is very greater than a, that time a is almost equal to 0, right? So what will be this? A will be 0 means E axial is equal to k into p into 2x divided by, if a is 0, it will be x square the whole square, which is equal to k into p into 2x divided by x to the power 4. This becomes 3. So it is k p axial is equal to 2 kp divided by x cube. Now let us study about equatorial points. So they are the points that lie on perpendicular bisector line of dipole. These are termed as equatorial points. We have 2 points here, plus q and minus q, and this is the distance between them, that is 2a. If this is 2a, this distance is a, and this is a point p which is lying outside this particular point, and here we have to calculate the dipole. And as we all know, electric field intensity from the plus q charge, it is directed in outward direction, right? And it extends up to say pn. And negative charge, it is directed radially inwards, right? It is directed radially inwards. This point p is lying on the perpendicular bisector of the line of this dipole. Suppose this is x. If this is x and if this is a, this distance is what? By Pythagoras theorem, it is x square plus a square. So if this is x square plus a square, this is also x square plus a square. Name them as a, b, and this is p. AP is acting in this direction along PN. Therefore, we will name it as E1. Okay, EAP is equal to E1, which is equal to KQ divided by x square. Here we have x square plus a square divided by root of x square plus a square to the whole square by Coulomb's law. This root and square gets cancelled. We are left with E1 vector is equal to k into q divided by x square plus a square. And we know that PB is acting along this direction, and this distance is also root of x square plus a square. So EPB is equal to E2, which is equal to KQ divided by, again, root of x square plus a square the whole square, and this root and square gets cancelled. We are left with E2 vector is equal to KQ divided by x square plus a square. So this E1 is acting along AP, and this E2 is acting along PB. We magnify this portion, what do we have? We have, this is our point P. So Pn is acting along this direction and Pb is acting along this direction. So this is represented by E1 and this is represented by E2. And this is making an angle of theta with respect to the vertical. So this is making an angle of theta with respect to vertical. So if we resolve this, what does this become? This becomes E1 cos theta. Vertical components becomes E1 sin theta And here for this becomes E2 cos theta, and this becomes E2 sin theta. Since we know that E1 cos theta and E2 cos theta, they are equal and opposite, so they cancel out the x components. These two get added up. Okay. Therefore, E equatorial is equal to E1 sin theta plus E2 sin theta. Magnitude of charges are same. Therefore, E1 is equal to E2. Therefore, this becomes 2 E1 sin theta. E1 is E1 is equal to, as we know, 2 into k into q divided by x square plus a square. And sin theta is what? This is theta. If you extend this, and if you also extend this point, this will be a, right? And this is our hypotenuse. So sin theta is equal to opposite. Okay, that is a divided by hypotenuse root of x square plus a square. Let us write down that. Therefore, 2 into k into q into a divided by, this is 1 and this is power is 1 by 2, x square plus a square to the power 3 by 2. You know that 2a is the distance between two charges and q is the magnitude of charge. So 2qa, can I write it as dipole? So this becomes k into dipole divided by x square plus a square to the power 3 by 2. E equatorial is equal to kp divided by x square plus a square to the power 3 by 2. Hence, in case if x is very greater than a, or a is very small, that time a can be equated to 0. The equation becomes E equatorial is equal to kp divided by x square to the power 3 by 2. 2 and 2 gets cancelled. We are left with kp divided by x cube. Now let us consider these 2 point charges. If, say for example, if this is minus q and if this is plus q, okay, and this is the distance between these two charges, and here F, that is electrostatic force, is acting in the downward direction because it is negative, that is minus q into E. Here the F is acting in the upward direction because it is positive. F is equal to plus q into E. Now what happens? Since there is a presence of electric field at this particular point, so there is a presence of electric field in this direction. So it experiences a uniform electric field, and since it is moving like this, torque is caused. Torque or rotation is caused. Now let us draw this diagram systematically. Since I said the rotation is going to take place, so if these are our two charges, minus q and plus q, they are separated by a distance of 2a from each other. And let us bring down this point as a and this point as b, and we know the distance between that is 2a, and we don't know what is here. And if this is making an angle of theta with respect to the horizontal, that force on AB, force on A is equal to QE in the direction of E. Okay, so this is the electric field E. So it is moving in this direction, right? A is in this direction, B is moving in this direction. So force, electrostatic force on B is QE opposite to direction E. The equation of torque tau, the force between these two charges is QE, and the perpendicular distance, that is this distance, we have to find out. So we already sin theta. Sin theta is opposite, that is AM divided by hypotenuse, that is AB, which is AM is equal to AB into sin theta. So what is AB here? AB is 2A sin theta. Now put this value here. This becomes QE into 2A sin theta We know that dipole moment is equal to product of charge to the distance between them. So q into 2a becomes dipole moment, that is p into e sine theta. For maximum, which is the product of dipole into the electric field. So, so maximum torque is at theta is equal to 90 degree. That is tau is equal to p into e sine theta, as we already know. If theta is 90 degree, that time sine 90 is 1, so it becomes tau is equal to pe. When when minimum torque is at theta is equal to 0, that means tau is equal to pe sine 0, which is 0 again. Theta is equal to very very small, that time sine theta is equal to theta, so tau becomes pe into theta. In our 11th, we have already studied that tau is equal to I into beta, where I is nothing but moment of inertia and beta is nothing but angular acceleration. So if this is our equation 1 and if this is our equation 2, let us equate 1 and 2. That means Pe into theta is equal to I into beta, where beta is equal to Pe theta upon I. So this is the equation for angular acceleration. So that the expression for angular acceleration beta is equal to, we have studied it in our first PU, that is we have studied in our 11th class. It is the product of square of angular velocity to the angular displacement. This is angular velocity, this is angular displacement. This is our equation 3, and if this is our equation 4, equate 3 and 4. So if we equate 3 and 4, Pe into theta is equal to Pe theta divided by I is equal to omega square theta. Theta and theta gets cancelled, so we are left with omega square is equal to Pe divided by I. So what is omega here? Omega is equal to under root P into E divided by I. We know that we know that we know that when the rotation happens, then the term exists called as time period. So omega is equal to 2 pi by t. We have studied it in our 11th class. So equate equation 5 and 6. What do we have here now? Root of Pe divided by I is equal to 2 pi divided by t. T is equal to 2 pi under root I by Pe. This is the expression for time period of an electric dipole in an uniform electric field.